So today we are doing chapter 6.3, the binomial model. So in section 6.2, we saw that the normal model applies to many real-life continuous numerical variables. The model that's most commonly used for discrete numerical variables is the binomial probability model. That's the focus of today's video. So remember that at the beginning of the semester, we talked about distinguishing between numerical and categorical variables, and also binary. Okay, so over here in the numerical category, now we've been talking about how we can break numerical variables into continuous and discrete. So the most popular model when you have a continuous variable, we use the normal model to talk about different probabilities. But when we have a discrete variable, we're going to be most often looking at a binomial model. And in our class, that's the only one we are going to be doing, binomial. So again, an emphasis on how important it is to correctly identify what type of variable you're working with. Okay, so we're working with with numerical variables that are discrete. The results of a random experiment may be modeled by the binomial probability model if the outcomes you are interested are counts. Okay, so that's going to clue us in if we're doing counts that we're going to be using the binomial model. How many heads did we see? Something like that when I'm talking about counts. So there are 4 characteristics that must be present for a binomial model to work, and we need to know and be able to assess whether the binomial model is appropriate. First, there must be a fixed number of trials. Okay, in other words, what's the probability of seeing 4 heads if a coin is flipped 10 times? 10 times is a fixed number of trials. In our binomial model, that's going to be represented by the letter N. You're only allowed to have 2 possible outcomes at each trial. So we're either going to have a success or a failure. So in the idea with the coin, we are going to count the heads as success. That's what we're interested in. If we don't get a head, then we're getting a tail, and that's a failure. There's only 2 possible outcomes. The probability of success is the same for every trial. So we're still flipping the same coin each time. The probability, if it's a fair coin, will be 1/2 every time to get the heads. This is important. It's represented by the letter P in the binomial model. And the fourth characteristic that we need to be true to use the binomial model is that the trials must be independent. In other words, the outcome of the previous trial does not affect the outcome of any of the other trials. So when you flip a coin, you know, the probability of getting a heads is not affected by whether you had a head the previous flip. So I've been using the coin example, and that is our first example here, but we'll go through it just quickly again. So an example of a random experiment that can be modeled by the binomial probability is flipping a fair coin 2 times and recording the number of heads. So if we were given this and we wanted to actually assess whether we can use the binomial model, we'd want to go through the 4 characteristics. Is there a fixed number of trials? Yes, it was given to us up there that said that we were flipping it 2 times. So there's 2 trials. Are there only 2 outcomes? Yes, this is a coin, so we have either heads or tails. Heads is our success. The probability of success is the same at each trial. We're getting that information right here where it says a fair coin, the probability is 1/2. It's going to be the same for each one. The trials are independent. And so that's going to be kind of something that you have to just kind of think about. And yes, that's going to be true when you flip a coin. So this will fit the binomial model. A second example that also fits the binomial model is rolling a fair coin and recording the number of ones. Okay, so this recording the number of ones is basically counting the number of times you roll a 1. Now that is the counting up of something is what's going to signal that we need the binomial model. Now let's see if it fits. So we roll a fair 6-sided coin, die 6 times. So 6 times, that's our fixed number of trials. There's 2 outcomes at each trial. So this one seems maybe a little bit trickier. There are only 2 outcomes because we're only interested in counting the number of times we roll a 1. So rolling a 1 would be considered a success, whereas rolling a 2, 3, 4, 5, or 6 would be considered a failure. So there's 2 outcomes. We either roll a 1 or we don't roll a 1. The probability of success is the same. We're rolling a fair 6-sided die, which means the probability of rolling a 1 is 1/6. And the trials are independent. Again, the outcome of one roll does not affect the outcome of another roll. So this works for the binomial distribution to be modeled by the binomial distribution. The binomial distribution depends only on 3 things. The number of trials, that's our N. P, the probability of seeing a success, and then, I'm sorry, only on, and the notation binomial NPX is what's used to represent the probability of getting X successes. So if you had the question up here, in this example here, what's the probability of rolling 2 1s if you roll a 6-sided die? I'm sorry, yeah, 6-sided die 6 times. We could write that as bin, right, for binomial. And then the next input that goes in is your fixed number of trials. That was 6. The probability of getting a success was 1/6. And the probability of interest that we were talking about is rolling 2 1s. So X would be equal to 2 in this case. And that is a way to write, that what I was saying, that the probability, what's the probability of rolling 2 1s if you roll a fair 6-sided die 6 times? So how do we find that probability? What is the probability of rolling 2 1s? So we're going to have several ways to find that probability. We could use the outcomes in a sample space, use a graph if it were given to us of the binomial probabilities, use technology such as StatCrunch, use a table of probabilities. So the table of probabilities for the binomial is in the back of this packet and in the back of your textbook and is required on the test to be used. So you'll be given this table on the test and you have to use it to find probabilities. So this is extremely important. Using StatCrunch is important. Also, these other 2 options. So the first 4 ways you should be able to read a graph, use the sample space, use StatCrunch, or use the table for this class. The final way, E, gives the formula for doing this. But this is, I'm not even going to go over it. This is not required for our class. Okay, so now we're going to go through these first four methods and actually figure out how to find these probabilities. The scenario that we're looking at is the probability of getting X number of heads when a fair coin is tossed 4 times. So note, this random experiment, flipping a fair coin 4 times and recording number of heads, can be modeled by the binomial model. So that's the first thing you always need to check. Is there a fixed number of trials? Yep, we just said n is equal to 4. There are only 2 outcomes possible, right? You can either get a heads or a tails. Check, that's met. The probability of the success is the same for each trial. Yes, it's half, 0.5. And the trials are independent because the outcome of one coin flip does not affect the outcome of the others. So the first method that we're looking at is using a sample space to list all the possible outcomes. Now, this isn't going to be a great method when our sample space is too big, but it's good for us to kind of get a feel for it. It's a good place to start. So this is our sample space here. All of our outcomes are written. You can see that there are 16 outcomes, 16 possible outcomes. All right, and now we can fill in our probability table down here. So what's the probability of seeing 0 heads? Well, that only happens one time up here. So right here, if we get all 4 tails, then we've seen 0 heads. And so the probability of that is 1/16, which is equal to 0.0625. The probability of seeing 1 head. So that's here in this column. We can see only 1 head. That happens 1, 2, 3, 4. So the probability of that happening is 4/16, which comes out to 0.25. The probability of seeing 2 heads. So 1, 2, 1, 2, 1, 2, all of those. Over here. Nope, not there. So all of these. So that's 6 out of 16. And that comes out to 0.375. The probability of seeing 3 heads, that's over here, 1, 2, 3, 1, 2, 3. So there's this column here. So that's 4/16, which is equal to 0.25 again. And finally, the probability of seeing 4 heads, looking for another color. So that's this one here. Again, only 1 out of 16, or 0.0625. So using the sample space, we're able to find the probability of all the different scenarios, the different counts, because we're counting the number of heads we're seeing. And what do these probabilities add up to in our table? They should add up to 16/16. They do add up to that, or 100%. We have the entire distribution listed here. The notation for this experiment using our binomial notation is given here. B for talking about the fixed number of trials. 0.5 is the probability of success, and X is the number of heads we're interested in knowing about. So if we're interested in knowing about the probability of getting 2 heads, we would put 2 in for X. And that we can read off of our table up here. So that's this scenario, right? And that is 0.375. Okay, so that's using the sample space method to find the probability. The next thing we're going to do is use these probabilities to actually draw a graph of the probability distribution. So along the vertical axis here is our probabilities. And down here is the counts, our number of heads that we're seeing. So 2 corresponds to the probability of seeing 2 heads. And that was 3.75. So we draw that like that. So the height of this line corresponds to the probability of flipping 2 heads. The probability of flipping 0 heads was 0.065. The probability of flipping 1 head, we calculated above, was 0.25. So the probability of flipping 3 heads was 0.25. And finally, the probability of flipping 4 heads was 0.025. I'm sorry, 0.0625. So StatCrunch creates tables like that. So we can see on the next page that we could get this output from StatCrunch. This is the binomial calculator. I'm just going to take a brief minute to show you where to find this on StatCrunch to help you with your homework. So if you click to StatCrunch and you go to Stat Calculators Binomial, this will come up. This is the default. If we want to modify it for our specific case, we had a fixed number of trials was 4. Our probability of success was 0.5. And now you can ask a bunch of different questions if you want to know different things. You have to modify whether you're talking about less than, greater than. We wanted to know the probability of equaling 2. And there is the actual graph that you're seeing in your notes. So you're able to use this to on your homework to find probabilities. The probability that we observe 2 heads is 0.375. And you can see that this bar is highlighted red to talk about that's what we were looking for. So you can use that on your homework, but also remember that you should practice using the tables, which we're about to get to, because on the test, you won't have StatCrunch. So it's a very useful tool, but you'll need to also be able to use the tables. So that's our next method. The following is an excerpt from the Table 3 binomial probabilities from the back of your textbook. So we just captured part of the tables here. I can't quite read all of the stuff. We need to use the rows of values that correspond to x equals 2 successes. I'm sorry, n equals 4 trials, x equals 2, and p equals 0.5. Okay, so we're being asked about right, our binomial was 4, comma, 0.5, and then x. And all of these things are on here. Remember that this is n and this is p. So here we see n, here we see p, and here we see x. So all of the pieces of information are on this table. So let's go through and find specifically what is going to be needed for ours. So our n is equal to 4. So we're starting right here. And our p is 0.5. So the distribution that we're looking at is right here, because I went from 0.5 down to the grouping that matched with the 4. This is where they kind of overlap, okay? And then over here are our x's that we were talking about. Right here's the x. So 0, 1, 2, 3, 4. The probability of seeing 0 heads is 0.062. That's what we calculated too when we did our sample space. So the whole distribution right here is laid out for you. And if you want to look up the probability of seeing 2 heads, that's when x is 2. You follow that over, and here it is, 0.375. So using this table is pretty straightforward and very important. As I said, you'll have to use it on the test. You can use this, right, to look up these probabilities and draw a probability distribution graph like we saw on the previous page. So the probability of seeing two heads when a fair coin is tossed 4 times is 0.375, which is not unexpected since we have just done that 4 different ways. What would happen if we changed the number of coin tosses? The probability of success, or okay, so we would have different n's and different p's, and the distribution would look a little bit different. That's not surprising. Let's compare what happens when we change n. Okay, so notice that we're still having, for both of them, it's a fair coin, but one we're going to have 2 fixed trials, and one we're going to flip our coin 4 times. Let's look to see how are these similar and how are they different. So here we have n equals 2, here we have n equals 4. They're similar in the fact that they're both unimodal, right? They kind of have this unimodal shape, and they're symmetric. So they're similar. They're different because they have the different number of outcomes, right? One is this one, you can have 0, 1, or 2 heads, whereas this one you can have 0, 1, 2, 3, or 4 heads. See? So there's a different number of outcomes. And also their centers are different. So notice this one's centered at 1, whereas this one's centered at 2. Okay? So that's something that we're seeing different. Now let's compare the binomial distributions for flipping a fair coin 10 times when the probability of success is 0.5 or when the probability is 0.1. So this time we keep the fixed number the same, but what we change is the probability of success. So on the left here, it's down here, this is the 0.5. On the right, we're seeing the 0.1. Now, how are they different or similar? So it turns out that this one is symmetric, right? But this one is skewed. So they're different. This one's skewed to the right. They're different because the probability is so low for a success. It's only 0.1. We're more likely to see a lot of failures. Like the probability of getting 0 heads is pretty high. The probability of getting only one head is very high. The probability of seeing 5 heads is very low because the probability of getting a head is so low. So we're more likely to see failures when we see this. Just, excuse me, just the opposite if we actually had the probability of success being 0.9, now we're seeing something skewed to the left. And we're much more likely to see successes. Look how big the probability is for getting 10 heads. It's the height of this bar, which is like about 0.35. That's pretty high. The probability of seeing all 10 flips giving you a head is 0.35. And that's because the probability of getting ahead is so high. So the binomial distribution can be described by its center and its spread. That's something we're familiar with, our mean and standard deviation. There's going to be some formulas to know that go with the binomial distribution, and you can calculate the mean and standard deviation if you know n and p. The mean tells us where the distribution balances, and the standard deviations, or as a reminder, tells us how far typically values are from the mean. So what do you think the mean is for these following distributions? So where do we think the distribution's balanced? Well, it looks like the mean would be probably at 1. And the standard deviation, if we were just to kind of estimate, maybe mean I'm saying would be 1, maybe standard deviation is about a half, right? The typical distance on average. Over here we might say the mean, this one looks like it's going to be 2, and the standard deviation maybe is 1, right? We're spread all the way out to 4 now. So again, these are just estimates. So let's actually learn what the formulas are and see how well we did by just kind of looking at this. The following binomial distribution is skewed to the right. Estimate the mean of this. Okay, so one more time, we're trying to estimate the mean. It looks like the balancing point might be around here, close to 5. So let's check this with our actual formula. The mean of the binomial distribution can be found with the following formula. So the mean is n times p. So it's the number of times you do your fixed trial times the probability of getting a success. So in this case, if we actually calculated it, mean equals n times p. 15 times 0.3 is equal to 5. So the mean is in fact 5. So if we go back and calculate the mean, let's do that here. I'm going to use our formula. Mean equals n times p. So that's 2 times 0.5 equals 1. Mean is equal to 4 times 0.5. That's equal to 2. So those, we were pretty good on the means. Those are just what we expected. So n times p is how to find the mean of your binomial distribution. The standard deviation formula looks like this. Remember, sigma is our symbol for standard deviation, is n times p, so the number of fixed number of trials times the probability of a success, times 1 minus p, that's the probability of a failure, right, because they're the opposite of each other. And then we have to take the square root of it. So there's a little bit more to calculating that, but we can go through and work on that. So let's calculate the standard deviation for each of the following. For this one, we've already done. Mean is equal to 1. Sigma, standard deviation, square root, the n, which is 2, times our p, which is 0.5, that's the probability of success, times 1 minus p, which will also be 0.5, and this comes out to be 0.7071. So that's the average distance away we are from the mean. Next, mu, we said, was n times p, which is equal to 2. Sigma is going to be equal to the square root, 4 times 0.5 times 0.5. And that actually does come out to 1 for this one. So we expect to see approximately 2 heads, give or take 1 head. That's kind of how the mean and standard deviation work. And our last one down here, our mean is 5, we said, and our standard deviation will be our 15 times, times the probability of success times 1 minus the probability of success, which is the probability of failure, which equals 1.7748. Okay, so now we have a nice formula for calculating the mean and standard deviation of the binomial distribution. And the last thing is, let's use this binomial distribution to work on this problem. So the most common application of the binomial model is in survey sampling. So imagine you have a large population of people, such as 100 million registered voters. Let's assume 50% of them will vote Democratic candidate in the next presidential election. Suppose ABC News excuse me, takes a random sample. Okay, that's probably going to be a word we're going to care about. They're taking a random sample of 100 voters and ask them which candidate they're going to vote for. So sounds like these are some important things. We've got 50% will vote Democratic. They are taking a random sample of 100 voters and ask them which candidate they're going to vote for. So now we can look at what we'd expect to see in our distribution. So, but before we do this, we need to see, is the binomial model appropriate? So we have do we have a fixed number of trials? Yes. We're asking 100 people a yes or no question, right? There are 2 outcomes. Yes, this is true, right? We're going to call success being voting for a Democratic candidate, and then anything else that anybody else that they're voting for is going to be the failure. So it would be 1 success, failure would be all others. The probability of success is the same at each trial. Yes, it said up here that 50%, they assume that 50% will vote for the Democratic candidate, and if the sample is truly random, then they're going to be independent. So we've met our criteria to use the binomial model. Use the formulas for the mean and standard deviation of the binomial model to answer the following questions. How many registered voters in the sample should we expect to see vote for the Democratic candidate? So that's like mu is equal to n times p. 100 times 0.5 equals 50. We expect 50 voters to vote for the Democratic candidate. Give or take how many? This is asking us about sigma. Give or take, let's calculate sigma. Sigma is equal to 100, the square root of 100 times 0.5 times 0.5, which is equal to 5. So we could say that we expect to see 50 voters plus or minus 5 vote for the Democratic candidate. Would you be surprised if 60 voters in the sample indicated they would vote for the Democratic candidate? So would we be surprised if we saw 60 voters? No. I'd say no. We're within 2 standard deviations, or we're 2 standard deviations. That's not too unexpected. What about if we saw 70 voters say they're going to vote for the Democratic candidate? This would be surprising. This is 4 standard deviations away from what we expected. So that would be surprising. Typically, surveys refer to the percentage of voters rather than the number of voters when they report the results in the news. The binomial distribution would still apply. We're just converting it to percents. So it's more typical to see something, instead of seeing what we've just been doing, number of voters, we just said was 50 plus or minus 5, it's more typical for it to be percentage of voters and see it reported as, 50% plus or minus 5%. Okay, so that wraps up all of chapter 6. Remember the importance of knowing how to use the tables and which table to use when you're calculating a probability. Okay.